All right. Thank you all for being here. Let's resume the workshop. Now we're about to begin session 2 of the talks. The umbrella topic for papers in the session is adversarial machine learning for better security. So compared to the previous session where we dive deep to understand the adversaries, now we switch gear a bit into talking about security for machine learning. Or in other words, how do we make our models more robust and adaptable in an adversarial environment? We have excellent speakers from Amazon, Baidu, and Georgia Tech for this session. As a reminder, the format of the session is as follows. In the first 10 minutes, we will have a short 3-minute presentation for each of the papers. This then will be followed by a 20-minute Q&A session. Since the full pre-recorded talks are already available both on the KDD platform and on our YouTube channel, the live presentation is only meant to give a quick overview of the papers. There are 2 ways to ask questions. First, during and after the presentation, anyone can type in their questions in the chat window, and I will then read the questions during the Q&A session right after the presentation. When you do this, be sure to also include who the question is addressed to. The second method is if you want to ask questions directly. You can just mention in the chat window that you have a question. I will then call out your name during the Q&A session, and you can then ask the questions directly. So without further ado, I'll let our first speaker, Matt Butler from Amazon, present their work. Matt, go ahead.
Hi, I'm Matt Butler from Amazon. Let me just share my screen here. Hopefully everyone can see that.
We can see that.
Okay, great. So I'm Matt Butler from Amazon, and this is FraudFox, Adaptable Fraud Detection in the Real World, that I co-created with Yi Fan and Christos Philistos. And so just a bit of a motivating example here. So, how suspicious is Smith trying to buy $500 shoes at Monday on 3 a.m.? This is sort of a simple question that has a lot of complexity behind it that we try to tackle in this work. And so, given the multitude of variables that can be available, during that time, having to make split-second decisions at Amazon scale, and also be sensitive to changing business constraints that could be present. How do we deal with that type of complexity? So the overview of our solution, we sort of break it down into 4 different sub-problems. So first one being fraud adaptation. You can sort of think of this as like a supervised learning context. Anti-gaming, so this is dealing directly with that adversarial component, that David was kind of talking about in the keynote. The decision surface, so how do we take the information that we get from machine learning models and actually convert that into actions? And then business adaptation, how do we actually change to those different constraints that the business may have that sort of take our problem away just from a simple, binary classification problem. And so for fraud adaptation, this is, we tackle this one using a common filter approach, where we're integrating new class labels as we receive them. For the second subproblem, where we're dealing with the adversarial component, this is where we sort of have 2 different types of solutions that we detail in the paper. One with respect to how people tend to poke around the system, or fraudsters will poke around our system, trying to figure out where the holes are. And the second one is sort of more generally known as this non-stationarity. How do you deal with the non-stationary nature? So this is for like the chain data distributions. For subproblem 3, our decision surface. So for this, where we want to convert that information into actions that we can take, we look at it from sort of a cost-benefit analysis, where we can sort of derive this sort of optimal decision surface that will give us an opportunity to prioritize the type of orders that we want to look at. For subproblem 4, where we want to adapt to the changing business constraints, we consider sort of determining this sort of Pareto optimal set. So we look at a Pareto frontier of solutions, where each that are on that sort of the Pareto front are a set of non-dominated solutions given the different business constraints that we have. And from there, we can sort of bounce around to different optimal solutions, dependent on the constraints that are present at that time. Some of the results, we show a simulation first, where we have sort of this structural break in the time series. And in here, we show that the extended common filter with the non-stationary component that we propose in the paper adapts the quickest during those types of shocks within the simulation. More details obviously in the paper. And then in the real world, FraudFox has been implemented within a larger live fraud prevention system. And with this introduction, that's sort of the dashed black line there. There's a visible improvement in or reduction in the fraud losses. And with that, I'll say thank you, and we'll go on with the rest of the talks.
Okay. Thank you, Matt, for the presentation. Next, we move on to the next paper where we have Zhisheng from Baidu to do the presentation.
Hi, everyone. I'm going to share my screen. Can you hear me? Okay. So, let me start. Oh, hi, everyone. My name is Zhisheng Hu. I'm from Baidu Security, and this is a brief summary of our robustness improvement method for object detectors in safety critical scenarios. So it is very well known that deep neural network can have very good performance in many tasks, but their performance might drop when the inputs are subject to adversary perturbations. While there are a lot of efforts devoted to improving the robustness of image classifier, the robustness of object detectors has been ignored for a long time. But in fact, object detectors' robustness shall be equally important as the accuracy. We observe that object detector has widely been used to safety critical scenarios such as autonomous driving. And in such scenarios, any misperformance might lead to serious consequences. And second, we observe that previous work shows it's possible to improve the robustness of object detectors via adversary training. However, there's hardly any guidance of how to generate an adversary example efficiently and how to utilize them to perform efficient and effective adversary training. So those observations motivate us to study how to practically improve the robustness of real-world object detectors. And this intuition behind our work is actually augmenting the training data set with adversary examples. But how to do this in a large-scale object detectors is still challenging because the generation of this adversary example could be expensive. So basically, to overcome this challenge, we propose a two-stage adversary training. In the first stage, we train the whole model with weak adversary example. Here, weak adversary example is generated by our iterative PGD attacks with less iteration. So generating such a weak adversary example can be efficient and not expensive. But to avoid overfitting, we freeze the convolution layer and train the output layer in the second stage with only a small portion of scenario-based adversary example. And such adversary example can be expensive with large iterations to generate it. And such two-stage training can reduce the training time significantly, and then we can successfully deploy our method on university. So here I will show some example to compare our result with the pre-trained university. These images are all the perturbed images, and compared to the pre-trained university, our object detection model can correctly recognize all the objects, while some of these objects are missed by university. So basically, our proposed adversary training method want to practically improve the robustness of object detector, and here we use university as a running example. But there's still many work to be done in the future. For example, how to fully adapt our adaptive training to other attacks. But to sum up, we hope our work can now just serve as a stepping stone towards the efficient and effective robustness improvement for large-scale object detectors. And thank you very much for listening to my summary. I also invite you to the Q&A session. Thank you.
Thank you, Zhisheng. For our final talk in this session, we have Nathaniel Gould from Georgia Tech. Nathaniel, go ahead.
Okay, so share. I'm just trying to share my screen. I haven't actually used Zoom, so I need to set up. Okay. Is it good? Okay. Trying to get my screen. I can just give a, I guess, verbal overview.
Does the share screen button doesn't work for you?
I need the permissions, but it's not
Oh, okay.
going through.
But yeah, if that doesn't work, feel free to just do a verbal overview.
Yeah, so I did my research. So I'm from Georgia Tech, and this was while doing an internship at NTT. So I was researching the effect of using a GAN to generate adversarial examples to harden a DGA detection model. So what DGAs are they're used often by malware to pick addresses for their command and control servers. So malware needs an address for the attacker to either send instructions or to receive data from the malware. Now, they can use these DGA algorithms to dynamically choose new domain addresses. So let's say if one was found out, it could be replaced by a new domain and be unblacklisted, allowing it to function again. So for the proposed method, what we're doing is using a GAN, so a generative adversarial network that is trained on real domains to produce additional examples of adversarial, or malicious domains. So what we're doing is we're going to train a deep learning based classifier. So we used a LSTM and CNN based classifier, then training that GAN and using examples. So the GAN is a Wasserstein GAN with a gradient penalty. And I don't have any results to show up, but let me try sharing again. Okay, but yeah, so can't get the results up, but basically we, since we did testing on basically if it's a new domain, so we wanted to test the model to detect unseen malware variants. So we did this by, if we had, let's say, 15 DGA malware families, we would hold one out for testing and use the remainder for training. And then since this type of hold one out testing will have more variants, we did significance testing by running the testing 10 times. And then we got a confidence level for each family. And then we were able to, I believe it was 4 out of 5 or 4 out of 15 with significance saw an improvement. 2 out of the 15 showed a decrease in performance. And maybe during the Q&A, maybe I can, if I can get my permissions working, put up maybe just the table of results in the background.
Okay, yeah, that's fine.
Okay.
Yeah. Okay. Thank you, Nathaniel. Now we move on to the Q&A session. I think there's a first question for FraudFox. Why do we need multiple classifiers instead of one classifier? Is it related to the business adaptation?
It's certainly not related to business adaptation, and in fact, FraudFox, although it is an ensemble classifier, is only one of such fraud prevention systems within Amazon. So it sort of just augments one of our subsystems. And so the use of the multiple classifiers in this case was simply just taking advantage of ensemble learning in general, but by no means does it have to be an ensemble to take on the business constraints. Good question.
Okay. Thank you for the question and answer. To Zhisheng, I wonder if your approach can be viewed as an instance of curriculum learning, where we train on easy examples first before training on hard examples. David said one of his students has found that curriculum learning seems to be helpful for improving adversarial training of object classification.
Thank you, David, for the question. Yes, actually, this is a very interesting point of view. We can see our work as part of the implementation of this curriculum learning. And actually, your work actually inspired us to use the simple attacks first, and then use we call the strong adversary example later to train the object detection model. We did that, and we found this this order actually can help our retrained model to be better. Because we trained the other way around, but it didn't work as well as this one. So yes, I agree with your comment, and I think this is just one implementation on object detector. And I see another question.
Yeah, there's another question for Zhisheng from King Hao. When you talk about strong and weak class adversarial examples, I'm just curious, besides the parameters you controlled when generating these examples, do you use any metrics to measure the differences between strong and weak?
Yes, thank you, Jin, for the question. First, we control the parameters, the iteration number of our generating adversary example, and also we use success rate to measure how weak or how strong the example are. The details are shown in our paper. Basically, we choose 1,000, for example, we choose 1,000 weak example and 1,000 strong example. All these 1,000 other attack trials from the attacker. And then we test how many of these trials can fool our object detectors. So we use this success rate to justify it's weak or it's strong.
Okay, thank you. Next question is for Matt. Can attackers try to evade by performing frauds on products of small dollar amount?
Well, thank you. That's a good question. Of course, yeah, they can try. Yeah, so certainly, price of the item is a component of, that sort, when we showed that decision surface that we're creating. Price is certainly a component of that, but is not the, the sole factor, may not even be the most important factor, for a given order. And so just because something is a low dollar value doesn't necessarily mean that they'd be able to get away with it. And so a lot of other factors are taken into account when making that determination. Price can be one of them, though.
I just want to read off a comment by Christos Falutzos, which I believe as a collaborator at Matt's paper. Mm-hmm. He said, yes, they can evade detection, but they won't make much money either. Another question is for Zhisheng from Limin. Why the success rate of adversarial attack on object detection is so low? What do you think the fundamental difference between the common adversarial attack on image and the adversarial attack on object detection?
Thank you for the question. Actually, this is one of our observations. The success rate is actually not that low for object detector. That depends on how we use how we determine whether an attack is successful or not. Here in our paper, we only consider that the bounding box that with the misclassified labels as a successful attack. We didn't consider that the attacks that can for example, make the bounding box location to be different. So I think this might be one of the reasons that why the success rate is so low for our paper. I think in other papers or in some previous work, we consider difference between the object detectors and then the adversary on the image classifier. One thing is that the loss function is different for the object detector. We are not going to only consider the misclassified label. We also need to consider the loss brought by the wrong bounding boxes. But I'm not sure whether this is the fundamental difference. So I don't have actually a quite clear answer for now, but just for the observation, we see this actually is not as easy as to attacking image classifier. Hope this can answer part of the question.
Okay, thank you, Zhisheng. Next is a question from Jaren to Matt. So it's typical for Amazon to have flash sales and days of heavy consumerism that strongly differ from the norm. Does FraudFox take this into account? If not, what are some ideas for future work?
Great question. Yeah, thank you. And, this sort of talks a lot about what, and David was saying in our, during the keynote, where you sort of have anomalous behavior, but it's actually benign. And so this, obviously comes up when we have just a flood of traffic because there's a great sale on, or it's Prime Day or something like that. So in the way the FraudFox is designed currently, it's not necessarily that it would take that into account, other than that if it was taken into account in the training data as it was updated. But the structure of the approach does not necessarily tackle that question directly. But it would be something to consider for future work to improve its adaptation.
Actually, I do have a follow-up question on that. So the system presented for FraudFox is currently reactionary, or basically it waits for a change and then it adapts. Any thoughts on having some kind of adversarial way to probe the system so that it can be more preemptive?
Yeah, I thought that honeypot idea that someone put up earlier sounded quite interesting. But at present, no, you're right. It is very reactionary and is basically a function of what traffic we are seeing. But at present, it's not something we've tackled yet in terms of being more preemptive in terms of doing so.
Okay, thank you. There is a next question for also Matt from Needy.
Okay.
Wouldn't you have smaller data set on lower dollar value leading to bias in classifier? Multiple fraud attempt on smaller dollar value could lead to larger impact nonetheless.
Right. Yeah. So bias in the data set is probably one of the most challenging problems. I mean, I think in general, probably for security and defense and anything to do with an adversarial nature. And so a lot of what you'll see in FraudFox has to do with different ways of representing the data set. We can think of them as different hypotheses about what was generating that data for updating the classifier. And so absolutely, if you could have a whole lot of orders that are very similar, that are malicious, but then will never show up again, and that can kind of bias your classifier to looking for a certain type of pattern that is no longer relevant. And so we try to deal with that by sort of doing dynamic weighting policies for the classifiers, and that takes into account the couple of components we looked at in the paper: non-stationarity and this ability to poke around, where we try to focus on more than just the dollar value of an item, but also on a lot of other dimensions of what creates malicious or fraud-like behavior.
Okay, thank you. Next question is for Nathaniel from Zhong. The question is based on the pre-recorded talk. How much does the method depends on the 14 reverse engineered domain generation lags? Based on the examples shown that many attacks use a dash in the domain names.
Yeah, so it would, just how it's set up, depend on what you have in your domain set. So it's basically, since I used 14 domains and they were from reverse engineered algorithms, so I just used to generate 10,000 for each one, it would, the model's ability to detect the out-of-sample domain would depend on those chosen domains. So like, let's say if there were DGAs that were more similar to each other, they'd probably be able to generalize better to the out-of-sample one. So yeah, that's why I'm thinking some of the very low detection rates I saw that performed worse than the deep DGA random forest model are probably due to it not having any good examples of similar DGA domains or from the augmentation. So if there's no similarities, it probably couldn't generalize.
Okay, thank you. There is also another question for you, Nathaniel, from Limin. Is there some measurement study on an adoption rate of the DGA algorithm on PE malware and Android malware?
I'm not sure on that.
Okay, actually, I do have a follow-up question also for you. So in your work, the GAN is trained independent of malicious samples, right? Because it's trained to kind of generate more benign-looking samples. So it looks like you should be able to pair this data augmentation approach when training any malicious domain classifiers. Have you also looked at using this approach to detect other types of DGAs?
Well, in terms of different classifier, like just different model, yeah, but it's since the GAN's separate. So I did try using actually the same detection model from the GAN, but I couldn't get that working. But yeah, the GAN model is trained separately, and then you just use it to generate a list of domains. So I think I did 10,000 domains. So you could use it for to augment any sort of classifier, as long as it takes in, I used basically just the string as an input. So as long as it's using some sort of method on the string, it should work.
Okay, thank you. Any other question? If not, I actually have a question for Zhisheng. So intuitively, seems like not all samples will be equally important to be used as a source for adversarial modification for retraining, right? Any
Yes.
thoughts on sample selection?
Yes, actually, thank you for this question. This is actually one of the critical part of our paper. We consider the scenario-based examples. For example, when we consider the autonomous driving scenario, we only choose the image, for example, from the Google data set as the supercategory, outdoor or vehicle. So we use this kind of image to generate an adversarial example and then do the adversarial training. So for different scenario, we might choose different subset of this data set. And so this can reduce part of the adversarial training time, so that we can apply this method on a real large scale object detector.
Actually, as a sort of follow-up question on that. So one of the holy grail of adversarial sample retraining is to increase model accuracy, not just on the adversarially perturbed sample, but also on real samples, right?
Yes, yes.
So have you tried evaluating your models trained on COCO to some other object detection data set? That's not
we try, yeah, for our current stage, we only try this on COCO data set. And for the next step, actually, we are going to capture some real world data, for example, from simulator or for our upper vehicle capture images to test our method. But for right now, just for COCO data set.
Okay, thank you. Any other questions?
I think Nathaniel figured out the screen sharing. Maybe we can see the slides if that's already resolved.
I still couldn't get it. So I ran into this before with OBS, but I think it's like a bug in Catalina. So the permissions for like microphone and like camera show up, but then the screen recording one is just not there in the settings. So I think you have to restart and then rerun it like Zoom to get it to show up again.
Oh, that's okay. Maybe you can actually just paste the link to your pre-recorded talk on YouTube, actually. Maybe people can look at that instead, because we do have it on YouTube. While we're waiting for that, I actually do have another question for Matt. So when updating the model for adversarial adaptation by weighting samples close to the decision boundaries more, implicitly the goal is to just shift the decision boundary a bit, right? Because that's the implicit assumption of that. So any benefit of this as opposed to just try to estimate the most optimal boundary given all samples with some mechanism for, you know, robustness from outlier, obviously?
Well, yeah, it's a good question. So I'd have to say, like, within the work directly, we haven't looked at that trade-off, say, specifically. You know, there is a process by which we estimate sort of that optimal decision boundary for a given time period. And then as a function of that, we can use it to update the weights. So you can think of sometimes it maybe bouncing back and forth a bit between creating a set of weights to update a classifier, but then in the future, you may also be updating that optimal decision surface based on just as the environment changes. But, you know, say at any given time, you know, a direct experiment of looking at updating just the decision surface as opposed to updating the weights for the classifier, or FraudFox in this case, what wasn't considered, but would be interesting to try.
Okay. Yeah, I think thank you all for the great participation during this session. I think that's all the talks and the time that we have for the Q&A. Next, I'll hand this over to Gong for our next session. Gong, go ahead.